Bengtsson from Stockholm University, and he will tell us about the existing problem of SIC-POVMS and why it matters.
Okay, thanks. So this is a problem that is not very well known, perhaps, but it's very simple to state. We're in a Hilbert space of dimension d. Then we take k unit vectors. K is some, for the moment, arbitrary number, and we insist that they form a resolution of the identity. I use a capital I for the index here. So this should be proportional to the identity. And if you take the trace of this, you can calculate that this real number alpha has to be equal to k over d. Such collections of vectors have a name, have two names. In quantum information theory, they're called POVMs. In signal processing, they are called tight frames. They simply call that. Now I'm going to put one more condition. I'm going to insist that when the unit vectors are different, I insist that their scalar products take the same absolute value. So there's a real number here. And then there is a phase factor, which is not specified by the definition. You can actually, if you square this and take traces, you can easily see that if you have k vectors obeying this, then alpha 2 has to be equal to something. You can calculate that. That's easy. It's k minus d divided by d times k minus 1. Collections of vectors obeying this, in quantum information theory, they are called symmetric POVMs. In signal processing, they are called equiangular tight frames. Now it's not hard to show that if you want to do that, then the smallest number of vectors you need to obey that is d. So the number of vectors is restricted like that. And the largest numbers of vectors you can have and have that, it's certainly bounded by d squared. Of course, this case, if k is minimal, is very well known. That's an ON basis. And that's obviously very important. If k is maximal, this is a case I'm going to talk about, then you have what people who work on it usually simply call the SIC. That's short for symmetric informational complete positive operator valued measures, and it's nicer to call them SICs, so I'll call them that. So this is what I'm going to talk about. It's an abbreviation. Look, I prefer to regard it as a noun. It was originally an acronym: symmetric, informationally complete, positive operator valued measures. But let's call them SIC. That's a nice name. They will be called maximal equiangular tight frames in signal processing.
What restricts the number of these vectors? You said
what restricts this? Well, it's not hard to see. If you want the resolution of the identity, you're going to need d vectors, otherwise it doesn't work. Yes. And it's clear that there's going to be an upper bound here, right? You can't.
This comes from this condition.
This condition, there will be an upper bound.
Because without this condition, you can have any number. Of course.
Okay. Yeah, but with this number here, you can have an infinite number, sure. But because of this condition, yeah. And it's not particularly hard to show that this is a number. I leave it at that. So the question is whether these things exist in arbitrary dimensions, and that's the whole question. It's easy to formulate. You may, of course, ask why one should want this. So some motivation for doing this. The original motivation had to do with quantum state tomography. And on the signal processing side, it has a lot to do with adaptive radar. I don't know too much about the signal processing business. The only thing I want to say here is that I went fairly recently to a workshop with people from signal processing and things. And then I was told that if I can find such a thing in dimension 2 to the 10, I should take out the patent because I would become rich. So apparently it's sort of useful there. But I don't care about the money, so I didn't go into it further. And I have a completely different motivation for why this is interesting. I'm coming to it. So how could one possibly find such things? It turns out to be very hard to actually find them. Maybe, so that I don't have to put references all the time, I should mention who are the main people in this game. So the main people in this game is Gerhard Sauner, who started it all, and then it was pursued by Andrew Scott, by Marcus Grassel, and by Marcus Appleby, and these are still the main players, so to say. Most interesting papers were written by them. Not all of them, but most of them. So in order to find such things, it seems natural to look for a group. Such that you imagine you have group elements, ui, they act on a special vector, and if you choose that special vector suitably, and you know the group, these things should form a SIC. This is a natural way to look for them, perhaps. And let the group be a unitary operator basis. What that means is that up to phase factors that should exist, well, we have to have this, right? There should exist d-squared group elements which form an orthonormal basis for the set of all operators acting on the Hilbert space. The set of all operators acting on a d-dimensional Hilbert space is in itself a d-squared dimensional Hilbert space, and you're asking for a group such that its group elements form an orthonormal basis there. That's called a unitary operator basis. This was introduced by Schwinger long ago, and it's been very much studied in connection with quantum error correction recently, which means that there are complete lists of these things of unitary operator basis for reasonable size of D. So one can start with that. The reason why one wants to use a unitary operator basis has to do with the fact that I'm not going to prove, but it's easy to prove actually. A unitary operator basis has a property that that if you do the following, to an arbitrary operator, then you actually get the trace of the operator times the unit matrix. And using this property, you can easily show that if you act with a unitary operator basis on an arbitrary vector, you necessarily get a POVM. This is not at all given, but this is trivial then. Okay. So the natural way to look for SICs is to fix a unitary operator basis, choose a vector, and then instead of checking all of those conditions, you check, I have just space to do that, you simply check these scalar products. And you want these to be alpha 2, and if k is d squared, alpha 2 actually comes out as 1 over the square root of d plus 1, and then there's a phase factor. So, okay. Now, anyway, people have looked, of course, numerically for solutions to this. In particular, Andrew Scott has looked for it numerically, and he has produced solutions by now. Solutions are known in every dimension up to 150, and also some higher dimensions, the record being 844. Once the numerical solutions are known, one knows a lot about their properties. It turns out that, well, here's a complete list of all the solutions that have been converted to exact solutions. And it's believed that the list is complete up to dimension 21. It's also complete in these dimensions. It's not complete here. The record is 323. So, the following observations can now be made. And I should say that the whole subject from now on is based on empirical observation. In other words, this is a data-driven subject. Everything that is known about SICs is basically known by analyzing the solutions that have turned up. There is no constructive procedure for constructing them. That's a problem. And I'll explain later why it's interesting. So, the group is the Weil-Heisenberg group. The group that generates SICs is a very special unitary operator basis. In fact, the one that was originally studied by Schwinger. And this group is a Weil-Heisenberg group. This group is defined as follows. You take two unitary operators, and you have a basis in Hilbert space. These are integers modulo d. And the first operator, so to say, translates you among the vectors. The second operator is diagonal in this representation, raised to the power I, where omega d is a root of unity. This is a group. Then you form all possible combinations of that. So the unitary operator basis that we use is actually up to a phase factor is simply all possible combinations of these things. This phase factor here is actually minus e to the I pi over d. It's convenient to use that phase factor, but I would prefer not to go into it. So, what?
Isn't there one x too many?
Pardon?
In the equation for x, isn't there too many x's? Do you need x on the other side?
Here? Oh, yes, there is. Definitely, definitely. Thanks. Good. Yeah, definitely. Yeah. So this is a unitary operator basis that produces SICs. With one exception, I should say. There exists one exception for which the group is different. It's probably not interesting. It's probably an exceptional case. Okay, we can let it stand, but this particular thing is an exception to the statement that the group is always the Weil-Heisenberg one. It's the only one that has been found. It's probably not important. Once you know that it's a Weil-Heisenberg group, what Andrew Scott does when he does this numerically is that he constructs a function which is basically which is 0 if and only if you choose a fiducial vector such that you get a SIC. And then, and this is sort of important, then he minimizes that function with, say, 10 decimals. He finds a solution. Afterwards, he refines it to like 200 or whatever decimals, or 500, as many as you like. And it never happens that the solution that he had in the first run goes away. In other words, SICs don't trick. If it's close to a SIC, it actually is a SIC, it seems. That's sort of nice to know. Once the numerical solutions are known, then you also know things about the symmetries of the solutions, what kind of unitary operators leave them invariant, and leave the SICs invariant, and so on. And then one can convert them to exact solutions. That's very hard. That's where Grassel and Appleby come in. And these are the cases where this has been done successfully. Now, with the understanding that we always use the Weil-Heisenberg group, we can rewrite the condition for things being a SIC as follows. This phase factor, which is not specified by the definition of the SIC, should be equal to this. Once you have the exact solution, and because we know the group, we can calculate these phase factors. And now comes a remarkable thing. These numbers turn out to be extremely interesting as numbers. And this is what I would like to sketch now. It turns out that when you actually calculate from an exact solution these numbers, they have very interesting properties. And now you can ask, it's a phase factor, so what would be an interesting phase factor? Yeah, so a possible answer, well, why don't you think about that while I wipe out a little here so that I can do more things later. Well, an answer that would be sort of cute would be if these phase factors were always roots of unity. That would be nice, right? It turns out that this is actually the case. Well, what would that mean from the point of view of numbers? That would mean that you belong to a particular number field. And so, because this is a physics seminar, and I'm still not really used to it, in Swedish and in German, fields have a better name. They call it Körper in German. I mean, nothing to do with fields, as we usually call them. Well, a famous number field is, of course, a set of rational numbers. Then you can consider what's called a cyclotomic field. This is a set of all numbers that are obtained in the following way. You take a rational number, and you take a root of unity, dimension d, say, or d, and you take another rational number, and you form this combination, and then you add and multiply and divide and subtract in all possible ways, and the set of numbers you obtain then is a cyclotomic field with generator omega d. That's sort of clear. So if these things were roots of unity, the conclusion would be that these numbers belong to a cyclotomic field. This is actually true in 3 cases. It's true for this one, the one that I don't like. It's also true for this one and this one. They are sort of trivial because the dimension is too low. In none of the other cases are we dealing with roots of unity here. I should draw your attention to the fact that roots of unity are pretty complicated objects in a way. Let us write omega 5. That's the 5th root of unity. If you actually want to know what that is, the answer is this. It's given by various nested square roots and things. If I write out omega 11, the 11th root of unity, in the same way, it would cover it would cover more than this, and it would involve not only square roots but 10th roots, and it's a horrible thing. Now the thing you actually observe here are horrible in just that particular way. The reason why we think roots of unity are nice is, of course, well, everything here is clearly geometry, because, well, we can define the following transcendental function, right? And then this thing simply becomes, you evaluate this transcendental function at a rational point. In other words, the reason why roots of unity are nice, why we like them, is that we happen to know that there is such an interesting function there. This was something that excited people in the 19th century, in particular Kronecker and Weber. And they made an interesting theory for cyclotomic fields. Unfortunately, that requires a lot of things, but in general, extending a field by adding new generators, so when we extend from rationals to cyclotomic, gives a Galois group. What Kronecker and Weber proved was that every Abelian extension of the rationals, so every extension you can get from the rational numbers by adding generators such that the Galois group is Abelian, is a subfield of some cyclotomic field. So that's a key result. And this choice of the integer here, the dth root of unity, is actually important, because if you have two cyclotomic fields with different d's, then one of them is a subfield of the other, provided the d of the first divides the d of the second. It's quite simple. D is called the conductor of the field. It decides, so to say, when one field is a subfield of the other. So this was a satisfactory theory. There are lots of Abelian extensions of Q. Examples of Abelian extensions of Q which are not cyclotomic is you add the square root of some integer, or maybe you add the square root of some negative integer as generators. So here you would put, instead, the square root of 2 perhaps, and then form all possible combinations, and you'd get this field. This would be Abelian fields. By this theorem, this is a subfield of some cyclotomic fields. If you ever came across something called Gauss sums, you may wonder why they exist, so to say. They basically exist because of this. Kronecker and Weber showed that anything like a square root of in this field can be expressed as a linear combination of things in this field. That's basically what Gauss sums are. That's a parenthesis. Anyway, when they had done that, Kronecker went on, and this is still very long ago. He started it, many other people continued it. He considered Abelian extensions of quadratic fields. In particular, he first extended the rationals by adding the square root of a negative integer, and then he asked for all possible extensions of that field which had an Abelian Galois group considered as extensions of that. These things may well be non-Abelian over Q. So that's a bigger set of possibilities. And after a lot of work by a lot of people, in the early part of the 19th century, there was a complete theory for this, which is sort of analogous to what we have here. Generators of these things, these Abelian extensions of imaginary quadratic fields, can be obtained by, you first fix an elliptic curve with some care. An elliptic curve is basically a torus, so to say, embedded in complex space. And then you choose special points on that torus. And then you have some fantastic transcendental functions, which are rather more sophisticated than just the exponential, and you get these generators of these fields. This was a theory. This was a great thing in number theory. It was referred to by Hilbert as the most beautiful part of science, and he emphasized not only of mathematics, but it's the most beautiful part of science. He was very impressed by it. So Hilbert then asked for a generalization of this. So he asked for a generalization of this Kronecker, Weber, etc. theory to Abelian extensions of arbitrary fields. This is Hilbert's 12th problem. In particular, you can ask for Abelian extensions of, if you take this quadratic field where this is positive. So he wanted a complete understanding of the Abelian extensions of real quadratic fields. And that should include something sort of like this, some sort of way of producing the generators of the resulting fields. This problem is still unsolved. This is one of the rather few Hilbert problems which is still unsolved. Lots of work has been done on it over the past 100 and something years, but it's unsolved. And this, of course, brings me to the point, which is that these things, let me take away this, because we already know that the group is the Heisenberg group. I'll stay with that just in case you. So let me write it here. This is something that was discovered in 2016 by Appleby, Flamia, McConnell, and Yard, with some previous works by Sauner and Julia Appleby. What I discovered was that these things that are calculated from these exact solutions, which are calculated with enormous computer power from using the numerical solutions by Andrew Scott, etc., as a basis, these things are generators of Abelian extensions of Q of precisely these things that are not solved by mathematicians for D equals the square free part. So if of D plus 1 over D minus 3. This is the observation. And D is the conductor of these fields. This is the central sort of thing that happened in 2016. And this is, I think, at the moment, actually the motivation for studying this problem. You may not every day think about Hilbert's 12 problems and so on and so forth. You have other things on your mind. But I think at the moment, this is the main motivation for studying this particular existence question. There are others, as I was hinting, but okay. And once this was known, lots of things began to happen. So lots of things happened last year. You should have, you know, wet things, but
Excuse me, so in the case of D equals 3, something important happens, right?
that's right. A good observation. Let me draw your attention. Let me not wipe out this. I will answer your question after restoring this. I always wipe out things that I need later. As I was pointing out, this and this are exceptions. They don't fall into this. These two are somehow too trivial to count. The interesting story starts at d equals to 4. So it's quite right. In dimension 3, these things don't happen. And actually the SIC here was actually found in 1844 by Otto Hesse, just for information. So this is a special case, quite. The story starts at dimension 4. Let me simply wipe out these things, and let me also wipe out this. And now there are no problems, right? Pardon? Yes, I should have told you. I forgot. Thank you. In dimension 12, there are two unitarily inequivalent solutions. They call 12a and 12b, because they have to be called something. These are Andrew Scott's labels. In dimension 15, there are 4 unitarily inequivalent solutions: 15a, 15b, 15c, 15d. And they differ in various interesting ways. This is a particularly symmetric solution. These are sort of on the same level. And yeah, when you worked on this after a while, all these things, 7b is wonderful. 19e has a fantastically high symmetry, and so on. You know, you get familiar with these things. But the labels are like spectral classes of stars. You know, stars are labeled by O, B, A, F, G, K, G, K, M. Right, and there's no reason for it, and there's no reason for why these labels have been chosen. No.
Is it twice actually? Because maybe there will be a dimension in which there will be more solutions than letters.
Yeah, that is correct. You have to ask this question for Andrew Scott. He's getting up to J, and I think for 63, where only the numerical solutions are known, so they're not listed here, it goes up to P, I think. So he's getting close to it. Yes. Any criticism of this labeling system has to be directed to Andrew Scott, not to me. Anyway, once this central observation was found, lots of things started to happen. You say, okay, let me take away this because oh, it's wet. For instance, well, yeah, so this means that SICs are organized in classes. We organize them by the dimension in which they find. But then the number theory sort of has to do with this capital D here, and that's a square-free part, because only the square root of this thing occurs here, of this thing. So you can have two different D's here, which gives the same capital D, right? And that should mean that the SICs in those different dimensions should be related. Actually, a quick calculation reveals the following. If you change little d to d times d minus 2, then the capital D, which was d plus 1 over d minus 3, it's a pleasant calculation to show that this now goes over to a square of something times what it was from the start. And since what comes in here is only the square-free part, this means that capital D doesn't change when you do this. So there's an organizing principle here. If we start in dimension 4, capital D is then square root of 5 times 1, which is 5. So this would be the set of SICs that have to do with extensions of the quadratic field to do with square root of 5. Then you get the following. When you do this maneuver, you get to 8. Then actually it turns out that 19, if you try to calculate in your head, also has the same capital D. On the other hand, 4 divides 8, and since D is a conductor of the field, that means that the field that comes in here contains that field. This is a subfield of that. On the other hand, 4 doesn't contain 19, so although the fields here are related, it's not the case that this is a subfield of that, so I don't draw an arrow. Then the next thing, as you move up here, is 48. And the next thing is actually 124, and that also doesn't divide, but 8 actually divides this, right? Yeah. Is this right? Or how can it do? No, it's like this, isn't it? So this actually divides that. And then the next thing that happens is 323. That's 19 times 17, so there's an arrow like that. This contains that as a subfield. And then there are further numbers, I think 844. And then comes something on this ladder, 2208. Well, yeah, and then it goes up, it continues to go, like. So these dimensions are sort of, this is how SICs are related. You will observe, incidentally, that among the exact solutions there, this one and this one is listed, and so is this one. So it's not by accident. These exact solutions were obtained after this pattern was known, and this pattern was utilized by Marcus Grassel to find them. And this was known, this has been found numerically, and it's also not by accident. This is a record. Andrew Scott looked at this thing because he knew it should be sort of simple, because it was sitting like that. And you can do similar towers from d equals 5. Then you start at 5, you get to 15, you get to 195, and there are other things in there, 53 and so on. It looks exactly the same, except that the numbers have changed. Okay, so this is how to organize SICs. This is the first observation. So the hope now is to, instead of trying to solve the whole existence problem, let us try to focus on an infinite set of dimensions. The idea would be, and I should tell you that we're not even close, but the hope would be that if you have a solution in dimension 4, you should be able to prove that there exists 1 in 8, 1 in 48, 1 in 2002, and maybe without even writing them, well, sort of. This gives a handle for how to think about things. Yeah. So this has to do with the number fields in which these overlap phase factors sit. But what is, so to say, the Hilbert space geometry for these SICs? How is it related to the Hilbert space? What does this mean? What does this pattern mean in terms of Hilbert space geometry? And here I can say something. I'll save this picture. This is where we want to go. We want to have such a picture of how these number fields occur, but it shouldn't be an elliptic curve here. It should be something else. Let me make a restriction, just for the sake, I mean, practical restriction, which will simplify my life. I'm going to tell you about the paper in which we actually didn't make that restriction, but let D be odd. That's actually, for some reason, even dimensions are qualitatively harder to work with than odd dimensions. So for the purposes of this talk, let me suppose that D be odd. So for instance, we could discuss those. Then D and D minus 2, I was saying that if you change D to D times D minus 2, then, well, we're looking for, if we're interested in, if we first look in dimension 5, then we're also interested in the dimension 5 times 3, and then 15 times 13, etc., are relatively prime. That has an interesting effect on the group theory. Then the Weil-Heisenberg group in dimension D times D minus 2, this group, which lies behind everything we do, actually splits as a direct product of the Weil-Heisenberg group in dimension D times the Weil-Heisenberg group in dimension D minus 2. And this means that we have a canonical way of writing the Hilbert space in which the dimension d times d minus 2 SIC sits as a tensor product of CD tensor CD minus 2. This now becomes sort of, say, a canonical way of writing this tensor product. Good. Then let me in particular focus on this then, since I restricted D to be even. So this would be for D, sorry, this is not capital, this is 3. Capital D is 3. Let's look at this sequence, for instance, for the sake of the argument. So what we do now is that we go home and we look at Andrew Scott's numerical solutions in various dimensions. And then we make the following observations. In dimension d times d minus 2, if you look at these numbers, then you will find that these phase factors, a particular subset of phase factors, namely this subset, is equal to 1. There is another particular subset where you put d minus 2 times I and d minus 2 times j. So here I and j run between 1 and d, so it's these squared things. These things are actually, with a minus sign, the squares of phase factors from dimension d. In other words, although the total number field here is bigger and contains this as a subfield, some of the particular numbers that sit here actually turn up in the SIC in the high dimension. And this pattern happens in in 19 plus 1 examples. The number of examples here is limited by the availability of exact solutions, of numerical solutions. We do this to 200 decimals or so. And I should say that the observation has considerable predictive value. I'm sort of pleased with that, because when we started this, Andrew Scott had one solution here. But we were able to, because we had made this observation, and we were, from this observation, we were able to draw a number of conclusions about what the SIC here should look like. So we were able to write to him and say that, okay, there are 4 solutions here, and this pattern should occur for all the solutions here, so that you should be able to find an additional 3 solutions here by looking numerically, and yeah, he found them. So a few of those were actually, sort of say, predictions verified by Andrew Scott. And this final thing, so when Marcus Grassel saw this, he realized only he can do such things. But if this is true, for this ladder, this thing was known only numerically, and because this is a fantastically symmetric thing, if there is such a pattern here, then I should be able to solve for this one exactly, and he did, and this is how he added this one to the. So there's a considerable predictive content in this, and it seems to be true. It's true everywhere where we've been able to check, including some clear-cut predictions that were verified. Moreover, we can prove it seems to be the case that pick any SIC. The precise statement that we want to make is pick any SIC in dimension D. So this could be 15A, B, C, or D, etc. Then there exists what we call an aligned SIC in dimension D times D minus T, for which this holds. This is, so to say, the observation. Then we can prove a number of theorems. If so, Then, for the aligned SIC in the higher dimension, we can prove the following theorems. One, if you take a SIC fiducial then in dimension d times d minus 2, and you take the partial trace over one of the factors, say you trace out the d-dimensional factors, as we usually do in quantum information theory, you get a reduced density matrix. And it turns out that this is a projector, proportional to a projector to dimension. This lives in dimension d minus 2 now, but the reduced density matrix actually has only d minus 1/2 Schmidt coefficients, and they're all equal. In other words, the entanglement properties of the aligned SICs are, well, they have surprising or at least interesting entanglement properties. Same thing happens, of course, if you trace out the other factor. Then we can also prove that each SIC in each vector in an aligned SIC is a member of two smaller equiangular tight frames. So there will be a set of this thing, it's getting confused, isn't it? This thing is a vector in a SIC of dimension d times d minus 2. That means I have d squared times d minus 2 squared vectors to play with. From these d squared times d minus 2 squared vectors, I can select d squared vectors. And they will sit in a d times d minus 2 over 2 dimensional subspace. So there